If you already designed a RAG pipeline, definitely you felt that the answers that you are retrieving through the vector similarity search are not totally reliable and something is missing. In order to solve this problem, you can use knowledge graph. So in this video, I will teach you how to design a knowledge graph for your RAG pipeline using Neo4j, Python, LangChain, and OpenAI API key. In order to design knowledge graph for your RAG pipeline, you need to collect and clean your data because you need a structured data. After that, same as what you were doing in the normal RAG system as a vector search, you need to chunk your data. Then you need to ingest your data to the knowledge graph. This includes ingesting the main nodes and all the relationship between those nodes. After that, when we have the text, we need to embed them. And after that, we retrieve them using LangChain. Data that I'm using today is the data for the history of Napoleon. This is a story that I'm really interested in it and includes the story of Napoleon, his minister, and the story of Battle of Waterloo. So these are two persons that are related to each other based on the history, and these two persons somehow involved in the Battle of Waterloo, which is an event. So let's dive into it and build a knowledge graph on top of this. So the first thing that we need is our knowledge graph. I first define a config file for the way that we need to get connected to the Neo4j. This config file helps us to connect to our Neo4j knowledge graph. And this Neo4j graph function is being called through the LangChain library. So as I mentioned earlier, the first step after we have the data is chunking the data. What this function does is just fetch the file that we have for our data and start chunking that file based on the size of the chunk that we decided to choose in this function. And this function is something that I'm fetching through the LangChain too. Recursive character text splitter is the most common way that you can chunk your data. However, there are other ways that you can also chunk your data. For example, based on the section or based on a specific character that you can search and study about it. Choosing the chunk size and overlap is really depend on the purpose of your project. If you're looking for a short response to your LLM, so a shorter chunk is something that you really need. However, if you are looking for a general response like 4 or 5 lines, then something around 600 with 200 overlap, it's gonna be enough for your LLM. The reason that I'm chunking the data is that at the same time that I want to design a graph RAG, I want to show you how to have a vector RAG inside Neo4j, because Neo4j has this ability that you can embed your data and pass it through the node and do the same thing that you're doing on other vector databases such as Pinecone in order to retrieve your data using vector similarity search. Now that we have our connection to Neo4j and a file for chunking the text, let's write our main function for the knowledge graph. What is happening here is that Neo4j use a query language named Cypher to pass all the information that you need inside your knowledge graph database. So what's happening here is that this graph is a connection to the knowledge graph and we can run our query using this function. This is the data that we want to ingest. This is the node name, the main name of the node that you want to create. Like we have person node, but each person has different value of the name, which is Napoleon and his prime minister. The second code that we need here is the function actually for ingesting each chunk. So what we do first is that we start chunking the main file and then ingesting all the text one by one to the chunk node. I need to do it so it's better for you to understand what is happening behind the scene. In this function also, we are using the graph to run the query. This is the connection to the Neo4j using LangChain that we defined in our config file. This is each chunk that I'm going to show you how we are chunking the file using this function. And then we define the node name and the node label for each chunks. And then we just run our function so it will start chunking and ingesting everything to the knowledge graph. Let's run these two functions for our pre-processing step. So what's happening in this part of the code? We are looping through each file of our data. We chunk it. We ingest the data as the main node, and then we ingest the chunks. Let's see what happens when we run this code. As you see, it started to chunking one by one and adding each chunk to the knowledge graph. This is our knowledge graph database, and these are the nodes that we created. As you see, this is the person node, this is the label of the node, and this is the name property that we defined. And this is the second person. We have the sections that each section is one part in our JSON data, which is carrier, general information, death of that person. We have also event node, that is Battle of Waterloo, and we have chunks. And if you see, each chunk is just a part of the main text that exists in each section. The next step is that we need to define the relationship, the way that these informations are related to each other. In order to create the relationship, I want to show you the cipher query that I use to create those relationships among the nodes. And here it's just a simple function to run those queries using our Neo4j connection. There are multiple relationships that we need between our nodes. The first relationship is person with person. The second one is person with section. The third is event node with section node. Fourth is section with chunk. And fifth is person to event. And some of these relationships are two ways. So the first thing that we do is that we add this relationship function here, and we comment this code because we don't want to run it again. However, just to let you know, Neo4j has a feature that even though if you run this code again, it won't ingest the duplicate value in your database. So we run our code again, so we have access to this function. So here is our first relationship. Match is something similar to select in the SQL query, and we are finding the two-person node where ID of the first node is larger than the second node. Why? Because we don't want the self relationship. That's why we need to have this condition, and then we merge them. Merge is a function that allows you to create those relationships between the first node and the second node. And since we have a two-way relationship, we do this from the first node to the second node and the second node to the first node. The second relationship is person with section, and we are doing this, we are matching these two nodes based on the property similarity. The name property in the person node is the same as the parent name in section node. Let me show you in the knowledge graph so you will understand it. So here we have the section node that has the property of parent name. And when we go to the person node, we have the property of the name, which is the same. And we are creating the relationship among these nodes based on this property. Third relationship is event and section, and same is based on the name and parent name. It's exactly same as the person and section. The next one is relationship between section and chunk, and how we define it is based on the type that is inside the section, the source inside the chunk, and parent name and node name. So there are two conditions here. Let's go back to Neo4j so you will understand it clearly that how this relationship is being done and why we need this. So something that is happening here is that this is the section, and this section, like general information, has a large corpus of information. Here we have chunks, that these chunks is related to the general information and is a part of the text. And also, if you see this, it's related to the Napoleon general information. The node name is Napoleon. And if we go back to section and we open the Napoleon, the parent name is Napoleon, is the same. So we have two properties that is similar to the property of this node, node name and source, and we match these two nodes based on these properties. And our last relationship is between person and event, and since nodes name are not the same, we don't need the condition of the ID here. The last step is to run all these queries together. Done. Relationships are created. Let's go back to the knowledge graph and see how the knowledge graph looks like now. So here we can see there are three relationships that have been added here. The first one is between section and all the nodes that exist here. The second one is that it's between sections and person nodes. Each person has, zoom in, each person has three sections, which is general information, carrier, and deaths. Same as Napoleon. However, for the event node, which is Battle of Waterloo, we have general information, consequence, combatant, and reason. The most important part is this. When we open it, you can see the connection between this section, which is reason, to all this chunk of text. So all this chunk of text is related to the section node, which is reason here. The reason that we had three relationships in our knowledge graph, but we have 5 different queries here is that if you look at this, we have related to relationship, has chunk relationship, and has section relationship. There are 3 relationships, but in 5 different conditions. That's why we have 5 queries here, but 3 relationships in our knowledge graph. The next step is to create a vector index. So vector index is something that allows you to do the similarity search. Even though we are designing a knowledge graph, but still you can use the similarity search power in the knowledge graph, same as what you can do in other vector databases such as Pinecone, Face, or ChromaDB. So we go back to our main code and we copy this function and import it here again. And I'm gonna comment this part of code too. So what we're going to do here is that we are creating a new index for all the chunk nodes. I chose the same name for index, but you can choose different name if you want. So what's happening here is that we are defining our index name, and Then this cipher query goes and creates a new vector index for the node that we are asking. We're passing the name here, that here right now is the chunk node. And here, this one is the property that all the embedded text will be saved there. So let's run this. And our last function that we need is the function that we embed all the text inside the chunks. The only thing that we are doing here is that we are passing the graph to run the query, we are passing the API keys, and the name of the node that we want to embed the text in it. Then it starts to fetching all those nodes that it doesn't have the property of embedded text, and one by one start to embed them. So let's add this also to our code. And it will start embedding all the chunks. So all our data is embedded. Let's go to the Neo4j and see how does it look like there. So let's refresh this. This is the chunk node. And now you see there is an embedding, text embedding OpenAI property that we defined, and it's embedded all the text in our chunk. Use this text and embedded all of them. Now that we embedded all the files, all the text inside the chunk node, we need to design the retrieving process. I am creating a new file named vectorrag.py and another file named graphrag. In vectorrag, we have one function that we pass the question to it, the index name that we created our index and named it as chunk, the node that index is on top of those nodes that again is chunk here in our project, and we have the vector source property and embedding property. Embedding is text embedding OpenAI, and this one is the text, the main source of that property. So now we're going to run our vectorrag and see what is the response. This is our code for running our vector similarity search. It's a simple rag. Up until now, we are not using any of the power of the graph to retrieve the information. Our question is that what was the Napoleon role in the Battle of Waterloo? Let's run this part of code and see the response. There we go. This is a response that is generated based on our vectorrag. But let's see what's the difference between this response and the graphrag response. So this is the function for generating the cipher query from the user query. What this function it does is that it gets the user query, and based on the existing schema and the prompt that you designed, it turns that query into a cipher query and fetch information based on the nodes and relationship. The prompt that we need to run this query, let me create a new folder here named LLM, and I pass the prompt into this. So I'm going to create a new folder here named LLM, and I pass the prompt into this. This is the prompt that I wrote to extract the information from our knowledge graph. Without these examples and the way that I'm explaining what kind of properties I have, the accuracy won't be that much. You really need to design a very, very good prompt if you want an accurate response from your knowledge graph. Now that we have everything, let's run our graph and see the difference in response. I just need to restart the kernel because I need to add my graph-rag function too. Okay, as you see, it's generating a cipher query based on this question. And here is the response. You can pause the video here and read these responses to understand the difference. And that's how it is. That's how you can design a knowledge graph for your RAG pipeline. However, you should know that this is not 100% accuracy. And the problem is that it's totally relied on the prompts that you're writing. Another way to increase the accuracy also is that here, when you fetch the information using the vector search, write another code and fetch all the parent nodes of that chunk that response is being retrieved. So you have more information in order to write a validation for your response, or just add those information to your final response. I hope that this video was useful, and see you in the next video.